Hello everyone, welcome to this presentation called Algorithms for the Solution of the Navier-Stokes Equations for Transient Incompressible Flows. So this is a lecture series that consists of two parts. In part 1, we talk about the projection methods, which use the Helmholtz and Hodge decomposition that allow us to decouple pressure and velocity fields in the Navier-Stokes equations. But in part 2, here I want to discuss about a very popular algorithm called the PISO algorithm. My name is Hugo Castillo Sanchez, and I want to describe the content of this presentation. First of all, I want to give a brief introduction to the finite volume method, which I already discussed in one of my previous videos. But the finite volume method will allow me to explain easily the PISO algorithm. Then I want to describe the temporal discretization used in this kind of methods, for instance, explicit Euler and implicit Euler. And lastly, we will talk about the PISO algorithm. So PISO stands for Pressure-Implicit with a split operator. We want to solve the Navier-Stokes equations for incompressible fluids, and these equations express mathematically the momentum and mass conservation for Newtonian fluids. In one of my previous videos that can be found in this channel, I gave a brief introduction to what is a Newtonian fluid. So in a few words, a Newtonian fluid is the simplest fluid that can be described mathematically. And for this kind of fluids, we observe a linear relationship between shear stress and shear rate. Shear stress is the force that is being applied over a surface of a fluid, and shear rate is the rate of change of the deformation. And for incompressible fluids, that means fluids such as water, where we do not observe a change in volume. For incompressible fluids with constant physical properties, we have these two equations. So the Navier-Stokes equations are a coupled system of partial differential equations. So we have equation 1, which expresses the continuity equation or the mass conservation that tells us that the divergence of the velocity field of the fluid has to be equal to 0. If this operation is different than 0, we no longer have an incompressible fluid. In equation 2, we have the momentum conservation equation, which is just basically Newton's second law applied to fluids. So you remember from your physics lecture, the Newton's law for bodies tells us that the momentum of a body, which is the product between mass and acceleration, that quantity has to be equal to the external forces acting on the body. And for fluids, we have something similar. On the left-hand side, we have accelerations, and on the right-hand side, we have forces acting on the fluid. So here in the terms to the left, we have the product between density of the fluid multiplied by two terms. The first term is a temporal derivative, which is the derivative of the velocity with respect to time. So this is some sort of acceleration. And then the second term is called the convective term, or a spatial acceleration, which this quantity expresses how the velocity changes in a space in the direction of the flow. And these two accelerations have to be equal to the forces acting on the fluid. So this first term is the pressure gradient that can be, for instance, affected by a mechanical device, such as a pump. So a pump is able to modify the pressure values of the fluid. This term is the Laplacian of the velocity multiplied by a physical quantity. So this is the diffusive term. So this quantity is the viscosity of the fluid. And then we have the second derivative of the velocity field. And then the last term is the source term. That means that those external forces that can affect the movement of the fluid, for instance, the gravitational forces or an external electromagnetic field, among other quantities. So these equations are expressed in bold letters. That means that we have vector quantities. So the velocity field is a vector quantity, and F can be, for instance, the vector, the gravitational vector. So as I was mentioning before, we have two physical quantities that are physical properties of the fluid. We have the density and the viscosity of the fluid. And then the velocity field depends on both position and time. So U is the velocity profile, and P is a scalar, is a gradient that also is also going to be dependent on position and time, and P is the pressure. So these two quantities are defined in a d-dimensional domain omega. So D can have dimensions of 2 and 3. So that means that we can solve these equations in 2, or even 1, 2, and 3-dimensional domains. So even though these equations it looks like we have two equations, but actually if we assume Cartesian coordinates, that means that our velocity profile will have three components: a velocity in x direction, a velocity in y direction, and a velocity in z direction. So these two equations are actually a system of 4 partial differential equations. So this is the full system of equations. So we have an equation of momentum for each velocity, one for ux, another for uy, and another one for uc. So we have temporal or temporal accelerations for each velocity. We also have spatial accelerations for each velocity. We also have pressure gradient terms, so that means that the pressure might vary in the 3 directions. Then we also have a Laplacian term for each velocity, and then the contribution from the source term. And then we have the continuity equation that expresses mass conservation. So let's talk about a bit about these equations. So the Navier-Stokes equations are a coupled system of 4 partial differential equations with 4 unknowns. You can count them. So we have 4 variables. So we have the 3 components of the velocity plus the pressure. And coupled means that we cannot know the value of these velocities without knowing the pressure value, and vice versa. We cannot know the value of the pressure if we don't know the values of the velocity. So as you can notice, these equations are expressed in terms of the velocity field, but there is no equation for pressure. If we were working with compressible fluids, that means gases, we could use an equation of a state. If you ever took some thermodynamic lectures, you might remember these equations for gases, such as ideal gas, van der Waals equation, Penck-Robinson equation. So these are equations of a state that can be used to compute the pressure. But remember, this talk is about incompressible fluids. So for this case, there is no equation for pressure. And as I was mentioning before, we have a strong coupling between velocity and pressure. And another important point is that in CFD, in computational fluid dynamics, the continuity equation is mostly used as a physical restriction of our system that must be satisfied. That means that if we solve these momentum equations for the velocity profile, the velocity components of our velocity profile have to satisfy the continuity equation. That means we must satisfy the mass conservation equation. So the finite volume method is a discretization technique, and the purpose of any discretization practice is to transform one or more partial differential equations into a system of algebraic equations. One of the features of the finite volume method is that it uses a continuum approach where the conservation principles are applied to solve partial differential equations in infinitesimal control volumes. So that means that, for instance, let's say you want to solve a flow problem in a channel flow or in a pipe. So your channel flow has specified dimensions. For instance, it has a height, it has a width, and it has a length. So you will split the whole domain into smaller cells or control volumes, and you will be solving the Navier-Stokes equations in each of the cells of your domain. And the finite volume method is the most popular discretization technique. The open source software called OpenFOAM uses this approach. So we wish to solve the Navier-Stokes equations for transient incompressible flows using the finite volume method. So I will be focusing first on the momentum conservation equation, because remember that I said that the continuity equation, which is this equation 1, will be used mostly as a physical restriction of the system that has to be satisfied. So on the meantime, let's just focus on the momentum conservation equation, which is this one. So I made some slight modifications to the momentum conservation equation, which is expressed a bit different. So here we have the temporal derivative, here the convective term. Here I include the density inside the operator, the divergence operator, and if you apply the chain rule into this term, you will end up with this same equation. So you can do the algebra, and then all the terms from the right hand side were moved into the left hand side of the equation. I also introduced the viscosity into the divergence operator. Also the source term is included as this term, because the source term can depend on the velocity and then the pressure gradient. So the finite volume method requires that this equation 3, has to be solved in each of the control volumes or in each of the cells of your domain. So for instance, here we have a domain that can be split in 3 cells. So we will be focusing on this cell, which has a centroid P. This cell has internal faces, and the finite volume method requires that this equation is satisfied over the control volume Vp around the point P. P is the centroid. So we have to solve the Navier-Stokes equation in integral form for each of the cells of your domain. So we have to satisfy equation 4 for each of the cells, for instance, for these 6 cells. Now, how do we discretize these terms of equation 4? So let's start with the simplest one, which is the source term. So when the source term is constant, for instance, where there is the presence of the gravitational forces, the volume integral can be solved easily. So if this is a constant, so the volume integral of a constant is just the constant multiplied by the volume of the cell, in this case, the volume of this cell here. On the other hand, if the source term is linear, for instance, FU can depend on a constant multiplied by the velocity field, then this integral becomes just simply as the product between the constant, the velocity at the centroid, multiplied by the volume. In my finite volume method video that can be found in my channel, we talk a bit more about these integrals. So I recommend you watching that video if you have not. Now, to discretize the diffusive term, which is the term that appears here, so we will use the divergence or the Gauss theorem, which allows us to transform a volume integral like this one into a surface integral over all the faces of the control volume. So this quantity is diffusive flux of momentum, and a flux can also be seen as a force per unit of area. So the divergence of a flux is a flow. So you will estimate this quantity in all points of your control volume, and if you sum this quantity in all points of your volume, you have the total quantity, this one, in the full volume of your cell, and that quantity has to be equal to the product, this product this product multiplied by the area or the surface in each of the faces of the control volume. So let's say we have this cell which has 6 faces, so you have to estimate this quantity, this this diffusive flux of momentum multiplied by the surface in each of the faces of the cell. This cell has 6 faces, so at the end you sum that product in the 6 faces of your volume, and that quantity has to be equal to this volume integral. So here n is the unit normal vector that points out of the control volume. So n is defined as this vector. It will point outwards. So this n will be different for each of the faces of your cell. So for instance, n will point out in this direction for this face. On the other hand, for this face, it will point out in this direction, and so on. And then the surface integral, this one, is reduced to a sum of the product, as I was saying before. This product where we have the viscosity multiplied by this vector S, which is just the surface or the area of the face of your control volume multiplied by the unit normal vector. And then you have this product, and then you have the interior product with the gradient of the velocity. So you have to evaluate this product in each of the faces of the control volume. So this surface integral becomes this simple algebraic expression. So you will have to sum all these products in each of the faces of the control volume. So F stands for phase. And then, remember, in the finite volume method, you will evaluate these gradients at the faces of your control volume. For the convective term, we follow a procedure similar to the one carried out for the diffusive term. So now, instead of considering this quantity, we will consider the convective term, which appears here in this equation 4. So similarly, this quantity expresses the convective flux of momentum. The divergence of a flux is a flow, so you sum all these flows in each of the points of your control volume, and that whole quantity has to be equal to this surface integral. So now you will have to estimate this quantity in each of the faces of your control volume. So the surface integral, this one, the one on the right hand side, is reduced to a sum of the product. The surface integral is reduced to the sum of the product F multiplied by U, where F is defined as the convective flux, which is just the product between this vector S that we define here, and then the interior product with this quantity, which is just the density multiplied by the velocity evaluated at the face of the cell. And then, this product FU has to be evaluated in each of the faces of the control volume. So this surface integral becomes just this quantity. You have to sum this product in each of the faces of the control volume. In the case of this cell, we have 6 faces, so you have to estimate this product and then sum it, and then you will have the surface integral that will be equivalent to this volume integral. So now our equation 4, if we substitute all these quantities that we obtain here, equation 7, we will consider a source term constant, so we will substitute equation 5, 7, and 9 into equation 4, and then we will end up with this equation 10. Now we only have to evaluate this temporal derivative that can be discretized as follows. It's just a simple discretization method scheme. The temporal derivative can be expressed as the difference between two velocities divided by the time step. Delta t is the time step. Here we have the velocity at the centroid of our cell. Here, this one, the centroid P. So we have to evaluate this velocity at the time n, where n represents the current time, or all time state, and n plus 1 represents the new solution. That means the velocity evaluated at t, the current time, plus the time step. So if we substitute this equation, this scheme, this temporal discretization scheme, into this equation 10, we obtain the following equation, which is easy to evaluate. We have equation 12. And now, how do we find, remember, our goal is to find the velocity field at the new time step. So we have to find a way to evaluate, to solve these algebraic equations. So we need to calculate, we need to know how we will evaluate the velocity field UF and its gradient at the faces of the cells of our domain. So it has been customary to neglect the variation of the phase values of the velocity and its gradients in time, which has led to the development of different methods of temporal discretization. And the most common one, or the simplest one, is explicit Euler discretization, where the values of the velocity and its gradient at the faces of the cell are determined from the all-time field. So that means that UF and its gradient will be evaluated as follows. We will consider a central difference scheme for this term, for the convective term, and the gradient will be evaluated as follows. So I have not discussed about the discretization of convective terms in my previous videos, but I'm planning to create a video where I will be focusing on talking about the discretization techniques applied to the convective terms. But here I'm using a very standard method where the velocity at the faces are just the velocity at the cell faces can be computed as follows, where we will obtain here the values. Let's say we want to estimate the velocity at this phase, in the one in blue. So we will only use an average between the velocity at the centroid L and the velocity at the centroid P. So this is how we evaluate the velocity at the cell faces, as an average. And the gradient also, it will be evaluated here at this cell face. So this gradient can be evaluated just using this algebraic equation, where we will use the value of the velocity in the neighbor minus the velocity at the centroid P divided by the distance between the centroids. So remember, these velocities will be evaluated are determined from the all-time field N. So D is the cell size, or the distance between the centroids. UN is the velocity. UN represents the velocity values at the cells neighboring cell P. So these convective and diffusive terms were discretized using standard methods. So in this way, if we substitute these equations into equation 12, we obtain equation 15, which is just an algebraic equation. So the velocity at the new time can be evaluated using this equation. So all the terms from the right-hand side depend only on the velocity values at time n, and therefore the new velocity, the velocity at the new time level, can be evaluated using a simple algebraic equation. So one of the major drawbacks of using this method is the Courant number, which is a very important dimensionless number used in computational fluid dynamics. So the Courant number is defined as the product between the velocity, a characteristic velocity, multiplied by a characteristic length. In this case, it can be the distance between centroids or the cell sizes, divided over delta t, which is the time step. So if we evaluate this Courant number, and if this Courant number is much greater than 1, the explicit Euler, which is equation 15, will become unstable. So that means that your solution, your numerical solutions can exhibit physical oscillations, which leads to unstable simulations. So in order to avoid that problem, we tend to use the implicit method, which is a stable scheme even if the current number is greater than 1. And also the implicit method will guarantee a bounded solution. That means a physical solution that will not transpass the physical boundaries. So the values of the velocity at the cell faces and the gradients at the cell faces will be estimated at the new time level n+1 instead of n. Remember, in explicit Euler, we evaluate the velocity and its gradient at the cell faces using the old time field, but in implicit, we will use the values of the velocity at the new time level. So we will use these equations instead. So therefore, if we substitute these equations into equation 12, we will end up with an equation 18. And for each control volume, we will obtain a similar equation. So yeah, remember, in finite volume method, we will solve the momentum conservation equation, in this case equation 12, for each of the cells. And for each cell, we will obtain an equation similar to equation 18. So I will explain what is the meaning of these terms. But what I wanted to say is that all these equations that you obtain for each of the cells of your domain can be assembled into a matrix system that will adopt the following form. So we have equation 19, which is a matrix system where A is a matrix of coefficients. A is also a sparse matrix, which means that the majority of the elements of the matrix are going to be 0. And then the coefficients AP, which appear here, will appear on the diagonal of the matrix A, while the coefficients AN will be outside of the diagonal. So the coefficients AN will include all the terms for each of the cells that are going to be neighbors of cell P. AP will include the contributions from all the terms corresponding to the velocity at the new time level. And also, U is the vector of unknowns, so that means the vector U will contain all the velocities at the cell centroids, and R is the source term vector. So the source term will include all the terms that can be evaluated without knowing the value of the velocity at n+1. And also the source term will also include all the terms that correspond to the previous time level. That means the velocities at the time level n. And once that we solve this matrix system, equation 19, we will obtain a new set of values. So that means we will obtain all the values of the velocity at the new time level. So the PISO algorithm, before explain the meaning, or what is the PISO algorithm. Remember, PISO stands for Pressure-Implicit with a split operator. So this PISO algorithm is used to deal with the Navier-Stokes equations for transient flows, where we have a strong coupling between pressure and velocity. So remember, a strong coupling between pressure and velocity means that we cannot know the value of velocity without knowing the value of pressure, and we cannot know the value of pressure without knowing the value of velocity. So to solve these equations, the idea of the PISO algorithm, or any algorithm, is that we need first to derive an equation for the pressure, and then we have to derive a corrector for the velocity field so that it satisfies the continuity equation. So I will explain this in more detail. But first, the first step of this kind of methods is that we need to express the momentum equation as equation 20. So remember, from our discretized equation 12, we can express this equation in a matrix system using the implicit method. And then you remember you have the product between matrix A multiplied by the vector of velocities, and then this product, this matrix product, will be expressed as this difference, and that has to be equal to the pressure gradient. So this is a semi-discretized form of the momentum conservation equation, since at this stage the pressure gradient will not be discretized. So don't worry about this, we will talk about this pressure gradient term later. So this matrix product can be expressed as these two terms. So the key step is to split the matrix coefficients of A into its diagonal and off-diagonal components. Here, AP, which is the matrix that appears here, is a matrix that contains the diagonal components of matrix A. So AP is a diagonal matrix. And then the matrix H will contain the coefficients for all neighbors here, multiplied by corresponding velocities evaluated at the new time level. And H, the matrix H, will also contain the source terms, including the source part of the transient term. So here it will appear the velocity at the all-time level divided by the time step. So the matrix H also can be evaluated explicitly from the matrix AP and the velocity from previous iterations. So from this equation, which appears here, equation 20, we can isolate this equation for H, and then we can obtain explicitly the matrix H by knowing the matrix AP and the velocity from previous iteration. So we will explain this in a more detail. All these ideas will come together in a few slides. And one of the advantages of using a diagonal matrix as AP is that this matrix can be easily inverted. So that means that the inverse of this matrix AP can be expressed as this matrix. And in this way, from this equation, U, the velocity of the vector of unknowns, the vector velocity, can be computed as follows. So from this equation, equation 20, where we have the pressure gradient, we can isolate this equation for the velocity, and then we end up with this equation 23. So the velocity, or the vector of unknowns, can be evaluated as using the matrix H, the matrix AP, and the pressure gradient term. So since we have now an equation for the velocity, we will substitute it in the continuity equation. So remember, the continuity equation is the divergence of the velocity field. So if we substitute the velocity field into this equation, we have equation 24. So you can see where we are leading, where we are going. So we will use equation 24 to obtain a Poisson equation for pressure. So yeah, this equation 24 can be expressed as equation 25. So from here we will obtain a Laplacian for the pressure. And the solution of the Poisson equation, that means equation 25, we will use these new values of pressure to correct the velocity field. So we will substitute the pressure gradient into this equation to obtain a corrected velocity. But here there is a problem. Once that we correct the velocity, the continuity equation is no longer satisfied, because we just use the new value of pressure gradient to obtain a new value of velocity, but it will no longer satisfy the continuity equation. And in addition, H also depends on the velocity that was just updated. So how do we solve this problem? So two approaches can be used. One of them is the simple algorithm, which will not be fully discussed here, or we can also use the PISO algorithm, which is the motivation of this presentation, which will be described below. So the PISO algorithm consists of different stages. So the first step is we need to solve the discretized momentum equation, which is the equation that appears here. So the pressure gradient is not known at this stage, but the value from the previous time step is used instead. So let's say we start by solving the momentum equation using the initial values of pressure. That means the initial conditions that we impose for the pressure field. So this stage is known as the momentum predictor. And the solution that we obtain from this equation, we will obtain an approximation of the new velocity field. And once that we calculate this new velocity field, we will use those velocity values to calculate h, that, remember, can be evaluated explicitly using equation 22. And then the pressure equation can be formulated. So once that we have h, we will obtain this equation 25, which is the Poisson equation for pressure. So this stage is known as the pressure solution. And then we have the next step. So the velocity field must be corrected using the value of the pressure gradient. And the velocity correction is carried out in an explicit manner. That means we will use the matrix H, the matrix AP, and the pressure gradient that was just obtained by solving equation 25. So this stage is called explicit velocity correction. But it can be noticed that the velocity correction consists of two parts. A correction due to the change in the pressure gradient here, and another one caused by the correction of neighboring velocities, which comes from the modification of matrix H. So this means that we also need to correct the term H, formulate the new pressure equation, and repeat the procedure. In other words, the PISO algorithm consists of a momentum predictor, which is solving the momentum equation once, and then followed by a series of pressure solutions and explicit velocity corrections. So that means that we need to solve first the momentum equation, and then we will use the velocity field obtained from the momentum predictor stage to compute the matrix H, and then to formulate the pressure equation, solve it to obtain the new pressure field, and use that pressure field to correct the velocity field. But we will not stop there. We will do the pressure solution stage and the explicit velocity correction stage many times until a predetermined tolerance is reached. So here I summarize all the PISO algorithm that I hope it gives you a clearer idea of how it works. So the first step is to initialize the pressure and the velocity fields at time t equal to 0. So that means that you will have to impose your initial conditions, and you will assign these initial condition values to Pn and Un. And then you will have to fix your boundary conditions. So for instance, if you are solving a channel flow problem, you have two walls, and then you will, let's say you want to have non-slip boundary conditions. So that means you will impose 0 values of the velocity at the walls or at your boundaries. And then you will have to specify the number of inner iterations for the interior loop. So that means you will have to assign a value to L. So that means how many times you want to do the pressure solution step and how many times you want to do the explicit velocity correction stage. And then you enter the temporal loop. So that means that you will be increasing the time by delta t. And then the first step of the temporal loop is that you will need to solve the momentum equation using this matrix system. So you will need your matrix AP, your initial velocity value, the matrix H, and then the pressure gradient evaluated at the cell faces at the all-time level. So this pressure gradient can be discretized very easily. And then you solve the momentum equation to compute an approximate velocity value u. So remember, this stage is called the momentum predictor. And then you enter the inner iteration loops. So you start with I equal to 0. And the first step of the inner iteration loop is that you will compute the new matrix H using, remember, this equation H. The matrix H can be evaluated explicitly. But now you will use the value of u that was calculated in step 1 here. And then once that you have matrix H, you can assemble the Poisson equation. Remember, using equation 25, you have matrix H, you have the matrix AP, and you solve this equation to find the pressure value at the new time level. So this is the pressure solution stage. And then the next step is that you have to correct the velocity using equation 26. So the velocity, can be evaluated as follows. So this is the explicit velocity correction stage. And then you increment the inner iteration index I by 1, and then you re-enter the interior loop until either the maximum number of iterations L is reached or a tolerance is reached. So you will repeat these 3 steps as many times as you have specified at the beginning, or until a specified tolerance is reached. And then once that you either reach the maximum number of iterations or the tolerance is reached, then you update all the fields to be used in the next temporal loop. So that means the values of velocity and pressure that you obtain at the end of the inner iteration loop will be the values that will be used in the next temporal loop. So you assign these quantities. So the new time level, the pressure and velocity at the new time level will be the old time, will be the velocity values at the old time level of the next temporal loop. And then you increment the time by delta t, and then you return to step 2 until the final time is reached. So this is the PISO algorithm summarized. So just final points I want to mention before concluding the talk. So the PISO algorithm is one of the most popular algorithms used by the open source software OpenFOAM. So this algorithm is used to solve the Navier-Stokes equations for transient flows. This is a suitable scheme that deals with the strong pressure velocity coupling in transient calculations. And this algorithm, this scheme offers stable simulations and also offers very accurate and stable results, and it requires less CPU time, but it might not be suitable for all processes. And the PISO algorithm consists of only one momentum predictor. So remember, this is very important. You only need to do this step only once. And then you will have to do L inner iterations that will do L pressure correction or pressure computations and L explicit velocity correction calculations for each delta t. And if the time step is sufficiently small, so that means the current number is much smaller than 1, we can use one momentum predictor and at least 2 inner iterations, and the system will converge. So the PISO algorithm is an extension of the simple algorithm. Simple stands for semi-implicit method for pressure link equations. So the main difference between simple and PISO is that simple does not consider the PISO interior loop. So in the simple algorithm, outer corrections are used instead. So after the explicit velocity correction stage, which is this stage, in simple algorithm, we go back all the way to the momentum predictor equation. So the simple algorithm does not consider the inner iteration loop. So simple algorithm, we do the momentum predictor, then we compute the matrix H, we do the pressure solution stage, the explicit velocity correction stage, and then we go back to the momentum predictor. And we repeat these 4 steps until a tolerance is reached. So that's the main difference between PISO and simple algorithm. So this procedure is an outer corrector, the one that I described before that. After the explicit velocity correction stage, we immediately go all the way back to the momentum predictor stage. Even though the simple algorithm looks inferior or looks much more simpler than the PISO algorithm, the simple algorithm can be used or is used to solve steady state flow problems. But in order to do that, we need to do some modifications to the Navier-Stokes equations, which I'm not going to cover in this presentation. So maybe in the future, I will be talking about the simple algorithm with more detail. But yeah, this is the end of this presentation. So I used as a reference the thesis, the doctoral thesis of Dr. Hazak, which can be found in the literature. So this thesis was published in 1996. So if you want to know more details about the PISO algorithm or other temporal discretization techniques, or you want to know more about the finite volume method, you can read his thesis. So with this, I conclude this lecture series that consists of 2 parts. Part 1, the projection methods, and part 2, the PISO algorithm. So thank you very much for staying here and watching my videos.